Modern physics is driving towards three specific engineering goals: hyperfast quantum computers, high-capacity quantum batteries, and nanoscale engines. But translating these concepts into working hardware hits a physical roadblock. We currently struggle to efficiently extract energy at a microscopic scale. This visual logic model maps out the golden rule of classical physics. For maximum efficiency, you first have to completely measure and document a system's exact starting state. Perfect starting data allows engineers to perfectly calibrate their approach, yielding an optimal energy extraction process. For centuries, classical thermodynamics followed a simple formula. To build a more efficient engine, engineers just needed more precise measuring tools. Scale down to the quantum level and that sequence breaks. Here, the act of measurement itself is the obstacle. Mapping a quantum state requires a massive logistics effort. It drains immense computational power, massive financial resources, just to log baseline data. Beyond the logistical cost, there is a physical disruption. The mere act of observing a quantum state collapses it, ruining the system before the extraction process can even begin. This creates a physical bottleneck, where the energy and resources spent trying to measure a quantum system far outweigh the power actually retrieved. Researchers have recently developed a smart protocol that removes the requirement for prior measurement. They are navigating the physics blindfolded. This diagram compares the two approaches. On the left, classical thermodynamics requires sequential steps: measure, then extract. On the right, the proposed method uses a single unified process. Instead of observing first, this concurrent model extracts energy while simultaneously learning its state in real time. This conceptual loophole renders traditional measurement unnecessary for high-efficiency extraction. Which raises a mechanical question. How does a physical system dynamically learn on the job without ever looking at its own individual state? Applied to a single, isolated quantum unit, the energy yield remains minimal. The protocol instead relies on a vast network of identical quantum systems operating simultaneously. Identifying broad, collective patterns across the group, it uses aggregate behavior to find the path of maximum efficiency. By shifting focus from individual precision to collective pattern recognition, the researchers turned the disadvantage of quantum blindness into a structural advantage. Science now possesses a universal method to extract the maximum possible energy from any quantum system. It removes the need to fully map or observe the underlying mechanics in order to exploit them. Because of this breakthrough, we can now optimally pull energy in the absolute dark and do it without ever sacrificing thermodynamic efficiency. Bypassing the measurement requirement bridges the gap between theoretical math and functional engineering. This protocol provides the operational framework necessary to build functional quantum batteries. The simultaneous learning and extraction model directly addresses the power management demands of commercial quantum computing arrays. Ultimately, bypassing the measurement paradox allows for the construction of real-world quantum machines that are both powerfully dynamic and completely efficient.